Okay, in our previous lectures, we developed the matrix equations of motion and came up with a matrix equation that looks like equation 1 that I'm showing you here. One thing I still want to remind you of, though, is what those terms entail. So we have here we have a mass matrix times a nodal acceleration vector plus a stiffness matrix times a nodal displacement vector is equal to a force vector. Okay. And I'll just remind you what the some of the terms in these matrices looked like. So in the mass matrix, for example, we had a term that looked like the integral over the volume of n times n transpose times rho dv. Okay, and inside this stiffness matrix Ke, we had a term that looked like the integral over the volume of, let's say, I'll just pick one integral, C11 times n partial with respect to x1 times n partial with respect to x1 transpose, right? Integral over the volume dv. Okay? And we had a similar terms for this force vector as well. So that's all well and good. The question we want to focus on now is how do we solve these types of integrals? Okay, so I'm going to remind you of something. Recall that these integrals and thus the equation, they're written on absolute coordinates. Okay, so recall equation 1 is written in terms of absolute coordinates. Okay, and what I mean by that, I'll say i.e. that means that when I write the term, for example, the partial of n with respect to x1, that looks like the partial of n with respect to x1, right? Okay, but we have a problem, right? But our interpolation functions that I gave you several lectures ago, those interpolation functions are defined on the natural coordinates, okay? Those natural coordinates are xi, eta, and zeta, right? And so what we have is we have n is actually, as we've defined it, is a function. It's a vector set that's defined as n, xi, eta, and zeta. Not that we couldn't write it some other way, but that's not how we've written it. Okay, so it's written as a function like this, not in as a function of, let's call them x1, x2, x3, like our integrals are in. Okay? Okay, so what do? Well, let's say that we potentially want to write the following. So we want to write, let's say in the case of the partial of n with respect to x1, right? So I'll write it out for you again. Partial of n with respect to x1. We want to write that maybe with the chain rule that says something like that's partial of n. Now with respect to xi, partial of xi with respect to x1 plus the partial of n with respect to eta times the partial of eta with respect to x1 plus the partial of n with respect to zeta times the partial of zeta with respect to x1, right? That would be a convenient way to approach the problem. So what's the issue? The issue is we don't have the natural coordinates in terms of x1, x2, and x3, right? So here's the problem with equation 2. Okay? We don't have the function, for example, that says xi is equal to xi times, xi of x1, x2, and x3, right? We don't have that. That's not how our natural coordinates are defined. Okay? So what do? So what we're going to do to solve this is we're actually going to map the integrals themselves to natural coordinates. Okay, so we're going to map the integrals to natural coordinates. Okay, and why do we do that? Is because it's going to put the integral in a form that's conducive to Gauss quadrature. Okay, so let me give you just a brief refresher of Gauss quadrature. So let's talk about it in 1D. Okay, so I'll just say that recall. Again, I'm assuming you've seen this before. That Gauss quadrature in 1D. So we'll start with a 1D case. Requires the domain of integration be from -1 to 1. Right? Such that, again, this is in 1D, we can write the following. If I have an integral from, let's say, x0 to x1 of the function f of x dx, that I can write that using Gauss quadrature and putting it into its natural coordinates as the integral from -1 to 1 of f bar of c now dc. Okay, I'm going to call that equation 3. Right? And what does f bar look like? Okay, so let's look at that. Where f bar of c, well, if I just do a substitution, f bar of c is going to look like f of x, which is a function of c, right? Times I have to convert this integral, so it'll be dx dc. Let's call that equation 4. Okay? Now, once we have it in this form, okay, so with the integral form of the right-hand side, Gauss quadrature can be used to approximate the integral. Right, and if we do that, we can write. Let's write the right-hand side here again. That the integral from -1 to 1 of f bar of c dc is going to be equal to. Maybe I shouldn't say equal to. Maybe I should say approximately equal to. And in some cases, it will be exactly equal to. But approximately, the sum from I equals 1 to n of w sub I f bar evaluated at c sub I. Okay? Let's call that equation 5. And then give you some definitions. C sub I, that's the location of what's called the integration point, or the quadrature point. Sometimes you'll hear them called Gauss points. And then W sub I is the quadrature weight. Now, in the intro class, we spent a long time talking about how we would compute those, but once you've computed them once, you don't have to compute them again, and you can just look them up in a table, okay? So I'll just remind you that in the intro class, we showed how to compute these. Okay, and the basic idea is we just force exact polynomial integration for increasing orders, okay? So what can we say is that an approximation that uses n Gauss points, or quadrature points, integrates a polynomial of order p equals 2n minus 1 or lower exactly. Okay? So for example, if I use 2 Gauss points, then 2 times 2 is 4 minus 1 gives me 3, so I can integrate a third order polynomial exactly with 2 Gauss points. Okay? And I'll just say that here we're going to just use pre-computed values. We're only going to really be focused on maybe 1 Gauss point or 2 Gauss points, right? So here we use pre-computed values that look like for n equals 1. So 1 Gauss point. It's just a midpoint problem. So we have that C1 equals 0, and the weight value of that is equal to 2. So in the case of n equals 2, c1 is equal to negative 1 over the square root of 3, and c2 is equal to 1 over the square root of 3, and then w1 is equal to w2 equals 1. Okay? So those are our pre-computed values. What about the case of double and triple integrals? Okay? So let's back out here. So in the case of multiple integrals, right, what we want to do, realizing that volume integral is a triple integral, so integral over the volume, I'm now expanding that out, of some function that is a function of x1, x2, and x3, right, dv, that is going to be integral now from negative 1 to 1, integral from negative 1 to 1, integral from negative 1 to 1. Now, similarly, it's going to be f bar of c, eta, and zeta, dxc, d eta, d zeta. Okay? Let's go ahead and call that equation 6. So the question that remains now is, what is f bar? And we do the same thing, right? So I'll just say where we can compute the following. We can say f bar of c, eta, and zeta is going to be equal to, we still have what we had in the 1D case, so it'll now be x1 as a function of c, eta, and zeta, x2 as a function of c, eta, and zeta, and then x3 as a function of c, eta, and zeta, right? So that hasn't changed. But instead of, if you remember let me scroll up really quick, we had, in the calculation here, we had f bar is equal to basically f, substituting these functions in here, times dx dx, right? But now we have a volume integral, and what we need is, we need to talk about what goes in front of this. And the answer is, we use what's called the Jacobian of the transformation, or rather the determinant of the Jacobian of the transformation. Okay, so I'm going to call this equation 7, and then I'll say here where J is defined as the Jacobian of the transformation, and it's going to be given as the determinant of the Jacobian matrix. Okay, so we could write that J is equal to the determinant of the Jacobian matrix J. Okay, call that equation 8. And what does that matrix look like? Okay, where this matrix J is just equal to, it's a 3 by 3 matrix. It looks like partial of x1 with respect to c, partial of x2 with respect to c, partial of x3 with respect to c, now partial of x1 with respect to eta, partial of x2 with respect to eta, and then partial of x3 with respect to eta, and then finally partial of x1 with respect to zeta, partial of x2 with respect to zeta, and finally partial of x3 with respect to zeta. Okay, so that's the 3 by 3 matrix that we have to take the determinant of. Okay, call that equation 9. Again, back to the intro class where I covered this at length, and hopefully whatever intro class you've taken has covered this too. There's a physical meaning to the Jacobian. If we looked, let's scroll back up really quick. What really is the Jacobian here? Dx over dx. What it really is, it's a ratio of length in the x domain to length in the xi domain, and the xi domain has always a length of 2, right? And so that's why So what it's really giving you is something of a stretch. How much is the space being stretched by? Okay, so in the 2D world, the Jacobian, if this was just, imagine this being a 2 by 2 matrix, the Jacobian, or the determinant of this matrix, is actually a measure of areal change, and then in the volumetric term, it's a measure of volume change, right? The original relative to the natural coordinates. Okay, so that's physically what the Jacobian is telling you. I'm not expecting you to derive why the determinant fits in there. I'm hoping that you remember that from your Calc 3 class, and just take it on faith that whenever we're doing an integral transformation, we have to multiply by the Jacobian to get that scaling to be proper. Okay, so that's where I want to stop here. We haven't finished the mapping yet. We're going to now take this information and go ahead and map the integrals and talk about how we can compute things like those derivatives, the partial of n with respect to x1, using this approach. Okay?